Okay, video's on. So older textbooks, at least back in my day when I learned, diagrammed electrons in their orbitals differently than the way they do it these days. I can't find any textbooks that do it any other way but this way, but let me show you my way, because I think it's way more intuitive. So as far as kind of any questions you get about electron configurations, you need to know this structure, and the way I usually tell you is just to memorize this one simple pattern. 1, 1, 3, 1, 3, 5. Let me do this. 1, 1, 3, 1, 3, 5. And I do mean just lines. 1, 1, 3, 1, 3, 5. Anytime you're dealing with electron configurations or structures of atoms, and you're trying to figure out some question about them, the first thing you can do is just literally write those lines down, and I'll show you what to do with them next. But I want you to picture this. Let's say that's the center of the atom, the nucleus, where the protons are. What this line really represents is not even a circle, a sphere. So I mean to be indicating, if I had a line here and I said, there's the one there, and this one is up that far, what I'm really indicating is a distance from the nucleus. So if this were sort of my zero line, this first sphere, so you've got the nucleus and the first sphere that you meet on the outside where there will be electrons going around in that sphere. This next one is another sphere, and then these three go together. I'll make them blue. There's another sphere, and so on. Like concentric circles, concentric spheres. You see what I'm saying? So when I say 1, 1, 3, 1, 3, 5, I'm really saying a distance from the nucleus, and these are the orbitals. So I think this 1, 1, 3, 1, 3, 5 system works better for visualizing what we're talking about. Let me redraw that a little more spaced. 1, 1, 1, 3, 1, 3, 5. So it always starts that way, electron configuration. 1, 1, 3, 1, 3, 5. Okay. Hydrogen atom, the first atom, has one proton in the nucleus. And for this whole discussion for now, think of this as the neutral atom, not the ions, gaining or losing electrons. Hydrogen has one proton in the nucleus, it has one electron. That electron, so if the nucleus is down here and this is that first sphere, I indicated an electron by making a kind of a half arrow like that. That's common to draw them that way. What you're looking at is the electron configuration of hydrogen. All right. Electron configuration of helium. 2 protons, 2 electrons. I'm going to pair the 2 electrons like that so they're together in this orbital. So now you've got a nucleus with 2 protons, and that first distance out, that first sphere out away from the nucleus, you've got 2 electrons together. And we say they're paired when we do this. If they're together on one line, the 2 electrons are paired. So I'm representing 2 electrons here. All right, that takes us from hydrogen to helium. Notice if you take helium and you slide it back over there to this side, you would have a full row on the left, and then you'll have a full row right next to it. If you picture the helium over there, just for now, this makes a little more sense. Because those first 2, not rows, columns, those first 2 columns are representing these types of orbitals. But I'll make that point better later. But once we've done helium, the number 3 atom the one that has 3 protons and 3 electrons, that's lithium. So that is the electron configuration of lithium. So far, this should all look very obvious. Don't overthink that. I can't really give you a good explanation why it splits up like this. That's quantum mechanics, and it's just too much to go into. But what's next after lithium? We're going to the right from lithium. Lithium is in the top left, just below hydrogen. Then the atom that has 4 protons and 4 electrons, that's beryllium. So I'm going to go here again and pair those up. That's the electron configuration of beryllium, Be. Next is boron. Boron has 5. So again, notice the 5. Boron has a 5 on it. That's 5 protons, 5 electrons for the neutral atom. So I'll do that. Go ahead and do this because no, it's not showing up. Okay, so boron, carbon, nitrogen, oxygen, fluorine, neon. Finishing out that row. 1, 2, 3, 4, 5. That's boron. 6 protons, 6 electrons. That's carbon. Nitrogen is next. 2, 4, 6, 7. So 7 protons, 7 electrons for the neutral atom. All right, now I filled these across without pairing them because they're all at the same level. So I fill these in and then I come back over here and I start doing this. So after nitrogen, we get to oxygen. So I do that for oxygen. Oxygen fluorine is this. And then when you get all the way to neon, that's this. That's the electron configuration for neon. Let me summarize again. This represents a sphere about this big around the nucleus. The next one up is another sphere out from the nucleus. These 3 are equivalent. You can picture those as, instead of a sphere, there's kind of an elongated orbital where the electrons are going up and down like this. That's one of these. There's another orbital that's going like this, kind of cigar-shaped instead of spherical. And then there's one going towards you and back. It's like the 3 axes, the X, Y, Z axes. That's what these 3 are. So you have spherical, orbital, and then these sort of cigar-shaped orbitals, could say dumbbell-shaped orbitals, going along each axis. And then the pattern repeats going up. But let me say something about this. We always point at these on the far right column, and say those are the noble gases. They're very inert, they don't react, very rarely react. The point is, when you have this single orbital, spherical orbital, and then these 3 filled like this, for one thing, they don't ionize. Everything's full here. Let me back up and say, that's what I had for fluorine. But let me back all the way up and say, I'll put these back. But I feel like this is a lot of words to say something that's kind of simple. If I said, hey, draw the electron configuration of fluorine, you would look at the periodic table and you'd see that 9 there, and then you'd go up to a piece of paper or whatever and you would go 1, 1, 3, 1, 3, 5. You would draw those. And then you would take that number 9 and go 1, 2, 3, 4, 5, 6, 7, 8, 9. There's the electron configuration of fluorine. So that caught us back up before I erased everything. Okay, so electron configuration of fluorine. Earlier in this semester, if I pointed at fluorine and said, what is the charge on fluorine when it's an ion? What would you tell me? Negative 1. And here's why. There's 9 protons in the nucleus, and there's 2, 4, 6, 8, 9 electrons. For the neutral fluorine, that's a 9. 9. But filling up this orbital and these 3 orbitals gives an atom a special sort of stability. So fluorine actually has this motivation to grab an extra electron. Now I've got 10 electrons and 9 protons. Electrons are negatively charged, so that gives it the -1 charge. You follow that? If I go on beyond neon and I go to the next one, sodium, there's sodium, and it has 11, 2, 4, 6, 8, 10, 11. 11 protons in the nucleus, 11 electrons. If I pointed at sodium a couple weeks ago and said, what's the charge on sodium when it's an ion, what would you say? +1. It loses the electron, again, to gain that awesome, perfect stability it gets from these being full. You see that? But neon, in between fluorine and sodium, naturally has that. It has 10 protons, 10 electrons, and here's the point. One of the things that makes sodium and fluorine react is they'll either gain or lose electrons, however they do, and then they'll be attracted to something, and they'll stick together, and then they'll make a compound. Neon has no motivation to gain or lose electrons. A, it's got this perfect stability, and B, it's balanced between its electrons and protons. There's no motivation for it to gain or lose electrons. That's why it's so stable. That's why it doesn't react. You see that? So one of the compounds I told you we study a lot are the ionic compounds. That's the charges. We'll talk about covalent compounds a little more and about how bonding works. But for covalent bonding, you need unpaired electrons. For instance, there's fluorine again, 9 protons, 9 electrons. You need the unpaired electron to do covalent. So that'll make a covalent compound. So again, let me go back and put neon here, the nice, full, perfect. No unpaired electrons, so it won't do covalent bonding. So it won't do ionic compounds, it won't do covalent compounds, aka molecules. That's the reason that whole right-hand column, we call them the noble gases. We always say they're inert, they don't react. This is why. Because you've got to have either unpaired electrons or extra electrons or deficient electrons so you get a charge for it to do something. I'll also point out that there is something the same about all the noble gases. If I just wanted to skip straight up from neon to argon, I would just do this. There's argon. There's these two full, that's argon. This won't gain or lose electrons, it doesn't have unpaired electrons. We're back to that bit of stability we've got. You see this? Now, I told you to picture helium over there filling that notch next to hydrogen. It turns out that just this very first single one, when only that is full, that turns out to have that same fundamental stability as those 3 being full, or full all the way up to these being full. So chemists just decided to put it over there because we frequently say this is the periodic table of the properties of the elements rather than the structure of the elements. So we put it over there because they have the same property as all the other ones. Doesn't tend to be reactive. But you probably already know there's H plus, it's just the proton, and there is such thing as H minus, but this is the weird one, it just kind of stands out. But it tends to have that same stability as having these full and as having these full. And in terms of having the same properties, let me do, there's lithium. One, 3, getting messy. 2, 3, 1. 1, 2, 3, 1. 3 and 1. Okay, that's lithium. And now I'm going to do sodium right below lithium. So the first electron in this little set, okay, and here's that little set here. All right. And then again, here's the upper set of the 1 and the 3. So the first one, this has the first one, and notice they're in the same column. Again, the same point, these have the same properties. These both have a tendency to lose that one electron and become one positive. Because they gain this stability down here, and this one gains this stability down here. And further up here, there's another 1, 3 at higher levels going further away from the nucleus. So you get that again, the next time you run into it, you're beyond lithium, you're beyond sodium, then you're down to K, potassium. Potassium, there will be this set way up here. Oh no. Potassium would be this next 1, 3 set. And if I back that off, what's next? Krypton? Yes. Krypton would have all these full, the next noble gas. So somewhere above this 1, 1, 3, 1, 3, 5 thing I've got, there are more up there to finish out the rest of the atoms. There's enough of these levels to fill up all the full periodic table. So what I'm getting at is the reason atoms are in the same column is because they have the same properties. First column, those all have one unpaired electron, and they all have a tendency to lose that one electron to gain the noble gas configuration. In the second column, they have the same number of unpaired electrons, and they lose the same number of electrons to get back to that stability. So their properties are defined by their structure, and their structure is elucidated in the periodic table. All right. What else to say here? I think it might be worth, well, I have to get to this. When did this go off?